Okay, good morning. We have been discussing about the vapor absorption refrigeration system in the last lecture, and we found that in case of vapor absorption refrigeration system, we will be having one refrigerant as the main working fluid, which will be passing through the condenser, expansion valve, and the evaporator, and we will be having another fluid which will be acting as absorbent for absorbing the vapor of the refrigerant. Okay, so the difference between the VCRS and vapor absorption refrigeration system is that here compressor is replaced by the combination of absorber, pump, generator, preheater, and pressure reducing valve. So if we add all these five components together, then we can replace the compressor of a VCRS system. Okay. However, the advantage of the vapor absorption refrigeration system is that uh, with vapor absorption refrigeration system, we can produce refrigeration by supplying negligible amount of high grade energy, and we can actually majorly supply input energy as low grade heat, and that heat can be easily available from the various waste sources of process industries and chemical plants, etc., or this heat can be produced from solar energy. Is this point clear? And if we analyze the thermodynamic performance of the system, so what we did for the schematic representation or for introducing the topic of VARS, I have taken the combination of ammonia and water over here, and for ammonia water system I explained you the entire cycle. And when we analyzed the performance of the system, we found that COP of vapor absorption system is nothing but efficiency of Carnot heat engine multiplied by, which is operating between generator temperature and condenser temperature, multiplied by COP of the reverse Carnot vapor compression refrigeration cycle, which is operating in between evaporator temperature and condenser temperature. So as we know that it is nothing but efficiency times COP of VCRS. So it means efficiency of any heat engine is always less than 1, because based on Kelvin Planck statement, we have to remove certain amount of heat to the heat sink, then only we can produce work in a continuous manner from the heat engine. Okay, so that's why efficiency value will always be less than 1 when some quantity having value less than 1 is getting multiplied with COP of vapor compression cycle, then ultimately the final value of COP will be actually less in comparison to COP of the vapor compression refrigeration cycle. But the only advantage is that we can operate this cycle with low grade energy, which is heat. Okay. Now, the whenever we will be doing detailed thermodynamic analysis of this cycle, so what we need to do, if I have to say find the enthalpy change across the absorber, enthalpy change across the pump, or enthalpy change across the generator, what we need to do? I'll be having particularly in absorber, in generator, pump, etc. I will be having mixture of ammonia and water. Okay, so ammonia and water is one example. There can be other combinations which can be used in this cycle, but at present let us stick to ammonia and water. Okay, so it means that if I have to analyze all these components, which are the additional components, in all these components actually instead of the presence of pure ammonia or pure water, we are having the presence of a mixture of ammonia and water. Okay, so it means that if I have to determine the thermodynamic properties of this mixture, then I must know what are the relevant thermodynamic principles and how using these principles actually we can establish the properties of the mixtures. Is this one clear? So let us talk about now the properties what these mixtures should have. So typically whenever we use the mixture of refrigerant and the absorber, we define these mixtures in two forms. Some are called as ideal mixtures. So of course there will be certain set of governing laws. The mixtures, the combination of refrigerant and absorbent which follows these laws, these are called as ideal mixtures, and the one which do not follows these laws, these are called as non-ideal mixture. And whenever we will be going to practical considerations, we will be having actually variety of non-ideal mixtures which we have to use. Okay, so let us start with very first thing. Very first thing is, let us talk about first the pressures. So you know, you have ammonia or you have water. Now I will not go to very specific things. I will start this discussion with A component and B component, and these two are forming a mixture of A plus B. Is this one clear? So whenever this mixture will be formed, there will be some key parameters which we need to consider. First parameter is that in the mixture there can be mass fraction. One important parameter. For example, 5 kg of A I have mixed in 10 kg of B. So I will be having total 15 kg mixture, but whatever the entire solution will be, we will be having, that solution will be having certain composition. For defining the composition of the solution, I can define one very important property which can be called as mass fraction. Is this one clear? So mass fraction of A, XA, will be equal to mass of A divided by total mass of the mixture, which will be MA plus MB. If I only have two constituents, then mixture mass will be MA plus MB. Similarly, if I have to calculate mass fraction of B, that will be simply equal to MB divided by MA plus MB. Is this one clear? Now, if I do the sum of XA plus XB, what I will be getting? XA plus XB will be simply becoming equal to 1. So it means if I have two constituents, their mass fraction, the sum of their mass fraction will always be equal to 1. So it means the mass fraction of second constituent will be nothing but equal to 1 minus mass fraction of the first constituent. This is a simple mass balance. Another important point could be that whenever I will be I will be producing the mixture, instead of mass fraction, I can use mole fraction for defining the concentration. Okay, ultimately what I am defining? I am defining the composition or concentration of the mixture. Okay, so other parameter could be mole fraction. So we know that number of moles of A will be nothing but equal to mass of A divided by molecular mass of A. Okay, likewise number of moles of B will be equal to mass of B divided by molecular mass of B. So from here I can define chi A, which is the mole fraction for A. That will be nothing but equal to Na divided by Na plus Nb. Total number of moles and number of moles of one particular substance. Likewise chi B will be Nb divided by Na plus Nb, and I will be having chi A plus chi B equal to 1. Is this one clear? All agree to this point? Now let us start with one very important law which will be very useful for constructing the property relations for the ideal mixtures. That particular law is called as Raoult's law. So any one of you know what Raoult's law says? Let's consider again A and B. So let us assume I have a container. In this container I have pure liquid A present. So this is pure liquid A. Then I have second container in which I have pure B present. So this entirely is filled with B. Then I have a third container in which partly I have A present, and then there is homogeneously mixed B also present with this. So it means it's a mixture of A plus B. Is this one clear? Now let us understand that whenever two A molecules will be here, so I will be having one molecule over here, one molecule over here. So these molecules will be having some intermolecular forces. Okay, it can be repulsive, it can be attractive depending upon the intermolecular distances, but there will be some intermolecular interactions between the molecules of substance A. Is this point clear? Likewise, in B also, between the molecules of B, I will be having some intermolecular interactions, and whenever I have the mixture of A and B, then in addition to intermolecular interactions between AA and BB, there will also be some intermolecular interactions between A and B. Is this point clear? All are agreeing to this point? Now, at present, for using the Raoult's law definition, let us assume that the intermolecular interactions between AA are equal to intermolecular interactions between BB, and this is nothing but equal to intermolecular interactions between A and B. All are clear with this point? So it means if two molecules of A, whatever behavior they shows in terms of interaction forces, same is the behavior for two B molecules and same is the behavior for molecule A and B. Is this point clear? What it means? It means that obviously when I have some liquid present in a, say I have water in glass, okay, so what happens? Some molecule of water basically goes into the vapor phase, and whenever these are in vapor phase, they apply certain pressure on that particular liquid. Is this one clear? That happens, okay. So likewise, when I have this pure liquid A, I will be having some molecules of A in the vapor state over here. All of you agree to this point? And of course, these molecules of A will be applying certain amount of pressure on this. Is this one clear? Now let us assume that we do not have anything other than A in this container. So if I do not have anything other than A in the container, then whatever the pressure that will be acting on this liquid, that entirely the pressure will be because of the all vapor molecules of substance A only. Is this point clear? And that is something which we call as vapor pressure P naught A. And this vapor pressure comes nothing but if I see the saturation pressure at the given temperature. It means the liquid is at temperature T. So if at temperature T from the property table I see saturation, if I see the saturation pressure, whatever will be the saturation pressure, that will be nothing but the vapor pressure of molecules A, which vapors of A are applying on its liquid at the interface. Is this point clear? Anyone is having any doubt about this? This is fundamental definition of the vapor pressure. Okay. Now, if I have B, then of course the vapor of B will also be here, and in pure B, whatever the pressure I will be getting, that will be nothing but P naught B. All of you agree to this point? Anyone is having any doubt? Okay. Now comes important point. When I have mixture of A and B, what will be happening? In the vapor, I will be having some vapor molecules of B and some vapor molecules of A. Is this point clear? All of you are agreed to this point? When you have a mixture and the mixture is having characteristics that the intermolecular interactions between A and B are same. So what it means? The escaping tendency of vapor molecules from the liquid solution will be same for A and B. So if molecules of A are escaping out of the liquid, then easily molecules of B can also escape with the same tendency. Okay. So if the intermolecular interactions are same, then both the molecular in the vapor medium, I will be having presence of both the molecules. Is this one clear? So it means that in this scenario, whatever the total pressure that will be acting on this mixture liquid, that will be the sum of partial pressure of A plus partial pressure of B. All of you agree to this point? Because if I talk about air, so if I have a glass of water, so glass of water, outside the glass of water there is air, and then there will be some water vapor molecules also. So that's why our total atmospheric pressure which acts on the glass that is nothing but equal to pressure of dry air plus pressure of the water vapor molecules. Okay, and typically it is called as partial pressure. And partial pressure is always less than the vapor pressure, because vapor pressure or saturation pressure will be coming into picture when only the entire that particular vapor is present and applying the total pressure. Is this point clear? So these are all very important concepts: partial pressure, vapor pressure, okay, and saturation pressure. So P I will be having nothing but PA plus P. Anyone is having any doubt about this? Because I have some vapor of A and some vapor of B. So vapor of A are applying partial pressure PA, vapor of B are applying partial pressure PB, and total pressure will be PA plus PB. Now there is one important law, which is Raoult's law, which says that if, say, in this mixture I have chi A as the mole fraction of A and chi B as the mole fraction of B, then as per the Raoult's law, PA, the partial pressure of A in the mixture, will be equal to nothing but mole fraction times its vapor pressure P0. Similarly, PB, partial pressure of B, will be nothing but equal to chi B into P0B. Is this one clear? So it will depend upon the mole fraction. So it means that for this mixture, if I plot mole fraction over here, say here my chi A is 0 and chi B is 1. Here chi A is 1 and chi B is 0. So what I will be having, and say this side is my pressure, I will be having somewhere over here, say this is my P0 V, vapor pressure of pure B substance, and here somewhere here I am having, say, P0 A, which is vapor pressure of pure A substance. Now at this particular point, because in the mixture I have pure B, so when I have pure B, pressure of A should be 0, and as it's a simple function of mole fraction and mole fraction is varying in this direction, so it will be nothing but a linear fit for representing the partial pressure of A in a mixture. Is this one clear? Similarly, I will be having this line which will be representing partial pressure of B at any mole fraction. All are clear with this point? And in this type of situation, the total pressure will always be sum of PA plus PB. Okay, so this is the pressure mole fraction diagram, particularly for a mixture which follows Raoult's law. Okay, so a mixture which is following Raoult's law, for which pressure is nothing but equal to mole fraction times P0 A. Now, for such mixtures which have same molecular interactions, whenever these mixtures are mixed together, these simply follow the volume conservation. What do you mean by volume conservation? It means volume of the mixture will be nothing but volume of substance A plus volume of substance B. So in such type of mixtures, there will not be any expansion or contraction of the mixture. Why? Because the molecular interactions between all combinations AA, BB and AB, these are actually of the same nature. Okay, so that's why whenever you will be mixing together, if molecular forces are same, these will neither repel each other nor these will attract each other. So whatever their individual pure behavior was there, same behavior will be there in the mixture. So that's why such fluids will be simply following the volume conservation. There will not be any contraction or expansion. Moreover, whenever we take this type of fluid and we mix these type of fluids together to form their mixture, these fluids do not absorb any energy or do not release any energy, and these simply mix together at the same temperature conditions. Okay, so it means that if you are mixing these together, say the temperature of initial temperature was Ti for both the liquids. Whenever you will be mixing together, these will be easily mixing. These will not require any additional heating or cooling, etc., in order to form the solution, and ultimately the final temperature will also remain the same. So it means this type of mixture do not require no heat absorption or release. Okay, so in this type of fluid there will not be any absorption or release of the heat. So if there is no absorption or release of the heat, then ultimately the final temperature of the mixture will remain same, and in order to form the mixture we need not to invest any energy. They themselves spontaneously will be forming the mixture. Okay, so the fluids or the liquids which follows all these three conditions, Raoult's law, volume conservation, no heat absorption or release, these type of mixtures are called as ideal mixtures. However, when we go into reality, it is not always possible to satisfy all the conditions, and of course in reality the intermolecular interactions between the molecules will be actually different. So that's why whenever we will be going into reality, always we will be finding the non-ideal mixture. So now let us discuss what could be the deviations which can take place over here to form non-ideal mixtures. Is this one clear? So first deviation could be that instead of having the attraction forces or equal interaction forces, say molecules usually have repelling behavior. What will happen if molecules have repelling behavior? There will be more tendency to escape the molecule. Okay, so if there is more tendency to escape the molecules, then ultimately the more number of molecules will be collected in the vapor phase. So if more number of molecules are collected in the vapor phase, it means it will be its partial pressure Pa will be greater than chi A into B. Similarly, partial pressure of B will be greater than chi B into P naught B. Is this one clear? So if molecules is having repelling tendency, then ultimately what will happen? The liquid will try to repel more and more molecule from the liquid phase. Why repelling tendency is not participating in the vapor phase? Can you tell me? Because it may so happen that if they are having repelling tendency, then vapor can also repel the molecule at the same rate to the liquid. Usually in the vapor phase, intermolecular distances are so large that the interaction forces between the molecules can be neglected. Is this one clear? So what happens in gaseous phase? In gaseous phase, molecules are at far distance from each other. So if these are at far distance from each other, the intermolecular interactions in the vapor phase are typically negligible. So that's why the repelling nature will be mostly affecting the intermolecular behavior only in the liquid phase. And if it is affecting only in the liquid phase, it means it will try to repel the vapor molecules from the it will try to repel the molecules from the liquid phase. Is this one clear? But in the vapor phase, because interactions are negligible, so this type of behavior will not make any difference. So that's why I will be having more accumulation of the vapor over the interface. So if I have more accumulation of the vapor, so partial pressure will be greater in comparison to the one which is defined by ideal law. Is this one clear? So that's why for this type of fluids, my pressure and composition diagram will be looking something like this. This is composition. P naught A here what will be happening? Positive deviation. It means because it has to be greater than chi A, so it will be like this. This will be like this, and it will be total pressure will be. So this will be actual PB, this will be actual PA, and this will be P equal to PA plus PB. So in the mixture state, because A and B are having repelling tendency towards each other, these will try to repel more and more molecules, and in the vapor phase it will not affect because of the negligible intermolecular interactions. Okay. Now let's talk about the other combination. What could be other combination? The molecules are having attractive behavior. If molecules are having attractive behavior, what will happen? Molecules will try to attract more molecules, so I will be having less vapor formation. So if I have less vapor formation, pressure will be lesser in comparison to the ideal situation. Okay, so PA will be less than chi A, P naught A. Similarly, PB will be less than chi B into P naught B. Can you draw the line now? It's very simple. What will be happening? What will be the actual behavior? Lesser than this, and this will also be less. Okay, so this will be the actual behavior. Anyone is having any doubt about this? So if I have repelling nature, there will be more pressure than the ideal law. If I have attractive nature, then there will be less pressure than the ideal pressure. All agree to this point? Now let's go to, after the discussion on the pressure composition, let's go to another aspect. So usually, if I have to define the thermodynamic property, what we do? We are having some values known, and then we utilize these values to refer to some property tables, and from the property tables we determine all other values. Okay. So typically if I have a simple compressible substance, for example water, okay. So what we do, if I have to determine the properties of water in the superheated state, then how many number of independent properties are needed? 2. Okay, pressure and temperature in the superheated state, or any other property, pressure and entropy. Okay, if for the same fluid I have to determine property in the saturated state, then how many are needed? Only one. Friction should be known, but at least by just knowing either pressure or temperature, I can determine all other properties in the vapor as well as the liquid phase. Okay. For mixture I need friction, but for independent phases only one property will be required. Okay. But whenever I have a liquid mixture, which is combination of A and B, if I have to define mixture properties in the superheated state, how many properties will be required? 3, because one more property should come into picture, which should define what is the composition of the mixture. Okay, so composition of the mixture will be coming as an additional property. So it means for a mixture in all the states other than the saturated states, 3 properties will be required, and out of the 3 properties, composition will be one important property which we should actually know in what composition this mixture is mixed. Okay, And whenever we are referring to saturated state, then at saturated state we will be requiring two properties. Is this one clear? So this is valid for mixtures, whereas for pure substances, other than saturated state we only require two properties, and in the saturated state we require one property. We simply know from our thermodynamics, we have referred many times refrigeration tables whenever we were solving the problems, and there we saw. Okay, so now let us discuss that temperature is my one property, pressure is my second property, and third property which I must take is composition. So composition, say I am taking in terms of mass fraction. So X is something which is representing over here composition. All of you agree to this point? Anyone is having any doubt? Now whenever we are having three properties, and if I have to represent these three properties on a two-dimensional plot, what are you doing nowadays? Every day you are so much involved in mobile phone, still they are not knowing, they are so much busy. What are you doing? Yesterday also you were very busy in the mobile phone. Is there any game? So T, P and third property is composition. Okay. So whenever I have to represent three properties on a two-dimensional plot, what I need to do? I need to fix any one property so that I can represent the variation of other two properties. Okay. So let me fix over here pressure. P I have fixed. For a given P, I will try to plot the temperature versus composition diagram. So this is T and this is X. Okay. Now here X is 0 and here X is 1. Here XB is 0 and XB is 1 and here XB is 0 for a mixture of A and B. Okay. So it means if I am referring to this point, here what I have? Pure B I am having. So at this point I will be having some boiling point. Let me represent the boiling point of B over here. So say this is the boiling point of pure B over here. Okay, is this one clear? So this temperature here is representing the boiling point of pure liquid B. At this point what we have? We have pure A. So whatever the boiling point here I am getting, that let me define as TA, which is nothing but boiling point of pure substance A. Now what I will be having, say I have taken arbitrary any composition over here, say XP. What will happen at XP? Say I was at this particular point. I have a mixture of A and B which is having composition XP, and I am at this point. Corresponding to this point I have some temperature. Now at the constant pressure condition I started heating this fluid. What will happen? At constant pressure, if I start heating the mixture which is having composition P, its temperature will start increasing. Its temperature will increase. Okay. And after certain point, at certain point of time, upon further heating, I will be finding that there will be appearance of some vapor bubble. Okay. So let us consider that when I started heating, at this point I have the presence of first vapor bubble during the heating process. Is this one clear? All of you agree to this point? Now whatever the experiment I have done over here, Same experiment I can do at some other composition xq also, at some other composition xr also, and corresponding to each composition I will be getting some value of temperature where this mixture, in this mixture the appearance of the first vapor bubble has taken place. Okay, so if I join for all the compositions the locus of these vapor bubble points, then I will be getting a curve which is called as bubble point curve or saturated liquid curve. Sorry? Because I am not talking about ideal mixtures. It can be any mixture. Okay, so whatever is the exact path of the curve, that we are not concerned at present. At present, I am just representing you that wherever I will be having the appearance of the first vapor, corresponding to that I will be having some temperature. Okay, and if I join the locus of all these, that is becoming some line which I can call as bubble point curve or saturated liquid curve. Sorry? No, at boiling point. This is boiling point of what? Pure B. This is boiling point of pure A. But at this point, am I having the pure B? I am having mixture of A and B. So when I have mixture of A and B, its boiling point can be any, more or less, anything. Okay, because I have a mixture now. Is this one clear? So that's why this represents nothing but the starting of the boiling at any composition. If I have a mixture in any composition. Is this point clear? All of you agree to this point? Now let's go to another scenario. Say at the same composition, I was at very high temperature where everything was in the vapor state. So inside the chamber everything was there in the vapor state. Okay. Now in this case, from this point if I start cooling under the constant pressure and constant composition conditions, what will happen? First temperature will decrease. I will be coming to some point where the formation of first droplet will appear in the mixture. The point at which first droplet will appear in the mixture, that is called as what? Dew point. Okay, that is called as dew point, and temperature corresponding to this will be nothing but the dew point temperature for a given composition. Now if I join the locus of all the dew points, again I will be getting a curve, and this curve will be representing dew point curve or saturated vapor state. Okay, bottom one is saturated liquid, this is saturated vapor, and in between these two I will be having the mixture of liquid plus vapor. Now there are two very important observations from this curve. First important observation is, for a pure substance what happens? The boiling point temperature and dew point temperature are same. Okay, is this point clear? We all know from for water what is boiling point at atmospheric pressure? 100 degrees Celsius. What is dew point? When condensation of water vapor starts, 100 degrees Celsius. So it means for a pure substance, boiling point and dew point happens at the same temperature. And what else? When we heat a substance in the saturated liquid state, at the saturated state, instead of change in temperature, its phase changes. During the heating process at the saturated state, temperature remains constant and the change of phase takes place. So same is true for B and A. Here you can see A is having the same thing and B is having the same thing. Boiling point and dew point are same. But whenever I am referring to the mixture, at any composition, my boiling point is different and dew point is different. So it means whenever I have a mixture, then for a mixture, the boiling point temperature and dew point temperatures will be different. And other important point is, if at the same composition you keep on continuing the cooling process, then in this cooling process what will happen? In between this I will be having mixture of liquid and vapor. But the important point is, during this phase change process for conversion of saturated vapor to saturated liquid, the temperature also decreases, and during the heating process temperature also increases. Okay, so it means for a mixture during the phase change process temperature does not remain constant. Again, very important statement. For a pure substance, during the phase change process temperature remains constant, but for a mixture during the boiling process temperature increases, phase change process, and during cooling process temperature decreases. So it means for a mixture during phase change temperature does not remain constant. All are clear with this point? Now third very important thing we will be formulating from this particular curve. Say at any arbitrary combination composition XS, I am at some point S over here. Now what I will be having at this point? At this point I will be having mixture of liquid and vapor. Is this one clear? At this point I will be having mixture of liquid and vapor. So if I go to my vessel, in the vessel I will be having liquid of A, liquid of B, and in the top vapor of B and vapor of A. Is this one clear? Anyone is having any doubt about this? If I refer to point S, what is point S? Point S is in the liquid plus vapor state. So if it is in the liquid plus vapor state, it means I will be having mixture of liquid and vapor. Liquid will be settled at the bottom, vapor will be at the top. So the liquid which is settling at the bottom, its state has to be equal to the saturated liquid condition, and the vapor which is present at the top, its state should be corresponding to saturated vapor condition. And at a particular point S, the temperature of the liquid and the temperature of the vapor should be same, then only it will be in thermodynamic equilibrium. All of you agree to this point? So this will be the physical situation of the container. So it means that if here also I have same temperature, here also I have same temperature, what I can do, I can fit over here a horizontal line. This horizontal line will be representing same temperature. Is this point clear? And this line is crossing saturated liquid line at this point and saturated vapor line at this point. It means whatever the vapor I am having over here, that vapor is having actually mass fraction of Xg, and whatever the liquid I am having at the bottom, it is having mass fraction of Xf. All of you agree to this point or not? Why mass fraction will be different? Because whenever we have formed a mixture, the two components of the mixture are having different boiling point. Okay, so upon heating or cooling process, one of the component will be boiling and other component may stay in the sensible zone only. That's why the temperature is also changing and phase is also changing. Is this point clear or not what I am trying to say? Okay. During the heating process, it may so happen that initially the boiling of the substance whose boiling point is less, its boiling will take place. So what will happen? In the liquid, the composition of that substance will be decreasing, and in the vapor phase, because more and more vapor of that substance are coming, so composition of that substance will be increasing. That's why for a two-phase mixture, during the boiling and condensation process, the composition of liquid and vapor is not same. For ensuring the thermodynamic equilibrium, the temperature is same. Okay, for temperature being same, I have drawn this line, but whatever vapor is there, that vapor will be corresponding to saturated vapor curve having composition Xg, and liquid will be corresponding to saturated liquid state having composition Xf. So here you can see the composition of one fluid is very less in the liquid and composition of that particular fluid is very high in the gas. It means that is the substance which is boiling rapidly in the mixture, and other one is just contributing in the sensible effect like increase or decrease of temperature. Is this point clear or not? This is very very important. That's why I am taking so much of time in this, because mixture properties, understanding of mixture properties is a bit difficult. This point is clear? So vapor will be having this composition and liquid will be having XF composition. Now let us try to relate it to some more physical parameter. Other physical parameter could be, let us consider that the total mass of the liquid and vapor phases in the entire mixture is M. We have one thermodynamic property which we call dryness friction. What is dryness friction? Please tell me. Let me represent it with symbol zeta. Dryness friction is nothing but mass of vapor divided by total mass. This is how dryness friction is written. Okay. Dryness friction is defined as nothing but mass of the vapor present in the mixture divided by total mass. Here I am not referring to mass of species A or species B. I am referring to total mass. Now let me write mass balance for species A. Mass balance for species A using the dryness friction. Okay. So how much mass of species A I will be having? Please tell me. If XS is my composition, what will be the mass of species A? XS into M, it will be the mass of species A, and this mass of species A has to be equal to mass of species A in the vapor phase plus mass of species A in the liquid phase. Okay. So how much is total vapor mass? Zeta into M is total vapor mass, and this vapor mass is having what composition of species A? Xg into Xg plus how much is liquid mass? 1 minus zeta into M. This is the liquid mass in this mixture. And what is the composition of this liquid? Composition of species A in the liquid? XF. So multiplied by XF. Okay. From here, M will be cancelling out, and what I will be getting? XS equal to zeta into xg plus xf minus zeta into xf, and from here zeta can be simply given as xs minus xf divided by xg minus xf. So this is how you can calculate the dryness fraction in a mixture. How I have written this mass balance, is it clear to you or not clear? Shall I explain it again? Again? Okay. So first you tell me, if I have some state which is having liquid plus vapor and having overall composition XS. XS is composition of species A. Then what will be mass of species A present over here? XS into M. Now this mass is divided into two segments. Part of mass is present in liquid state, part is present in vapor phase. First let us talk about total vapor mass. What will be total vapor mass? Zeta into M, because zeta definition is mv by m. So zeta into m will be total vapor mass, and this vapor mass is having composition of xg. So if I multiply xg over here, it is representing the mass of A in vapor phase. Is this point clear? And what will be liquid mass? If zeta into m is the mass of vapor, then 1 minus zeta into m will be mass of liquid, and multiplied by composition of liquid. Composition of liquid is xf. So it is representing mass of species A in liquid phase. So these two will be nothing but total mass of species. So from here, dryness fraction can be related to composition. Is this one clear? Anyone is having any doubt about this? Do you have class after this? Okay.